So welcome to Wednesday, second to last week of the quarter/semester. So we're rounding the curve. You only have, after today, you only have 7 more days with me until late January if you see me again. So we'll try to conclude with a bang, no pun intended here. We're going to talk about what is going on with the universe, okay? And we understand a lot about the universe based upon what this guy said, but we can also figure some things out by ourselves, okay? And a lot of that has to do with some of the things that we've looked at so far. So if you guys could, I want you to have your notes out, and you can pause the video now and get those and get your pencil sharpened and get a nice clean sheet of paper in your notebook so you understand the ideas we're going to talk about today. We're going to kind of wrap things up with a little bow here on this idea because we're rounding the corner towards the end of the chapter here. So if you could recall that we looked through spectroscopes. These weren't exactly high-tech devices, but they did the job because all they're trying to do is take light, and then because different wavelengths of light have they diffract differently, so that means that they spread out a little bit here. So what we see when we look through a spectroscope is we see that this light source, this is the light source from, let's say, a computer, we find out that it's actually comprised not of the whole spectrum of light here. It's actually comprised of just a couple bands here, and those bands represent different elements that are in this source of light. Now, this happens to be a computer screen, and you'll notice that all this computer screen is giving us, it's not giving us yellows or oranges or violets. All it's giving us is blue, red, and a couple reds and a green. And you recall, our eye receptors have blue and red color receptors and green color receptors. And if we get equal amounts of these, our brains are going to process that as being white light. Not total complete white light, but a close enough approximation that it works. But we can tell the element that is in here based upon that chemical signature. Different bands on a spectroscope represent different elements. And I can tell what's going on here with that when I look at these different bands here. So this is the distinct chemical signature of hydrogen gas, okay? And so if I look at what so there's emission spectrum and then absorption spectrum, but notice how this matches up. So this tells us that the sun contains, I can see where these line up, the sun contains hydrogen. I can tell that because this chemical signature is found in the sun. I can also tell that it contains helium because this band lines up here. I can see that it contains some helium. Each element is going to have a different chemical signature, and that helps us tell what elements are in the stars. So we're going to kind of put that in our back pocket for a second. So we're going to kind of take what's going to seem to be a left turn, but we're going to tie these two ideas together. So we're going to talk about something called the Doppler shift. And what the Doppler shift is, and again, this should go in your notes. If I'm putting it up here on my screen, you should be having this in your notes. So pause it if I go too fast. The Doppler shift is a change in the frequency of a wave due to motion. And remember, light is a wave, but sound is also a wave. So we're going to use sound to help us understand light. So think about this idea. How does the sound of an object change when it's approaching you compared to going away from you? Let's say it's an ambulance or a motorcycle. Does it sound the same, or does it sound different when it's coming towards you and going away from you? And so when you think about that, I want you to listen to this car. It's going to be honking its horn here. And as it's honking its horn, I want you to listen to how it sounds. So I hope you notice that the pitch changed. And the reason why the pitch changed is not because all of a sudden the horn itself made a different sound. It's because of your perspective related to that wave. So here I've got a jet that is moving and it's emitting a sound. And notice that if I'm on this side of the jet over here, that those wavelengths come at a more frequent rate and the wavelength is shorter. If I'm on this side, they come less frequently and the wavelength is longer. And as a result, I'm going to hear that as a difference in pitch. So this is kind of how I want you to visualize that. This is called the Doppler effect. If an object is approaching you or you are approaching that object, you're going to have a higher frequency and it's going to sound like it's a higher pitch. Where if it's going away from you, it's going to have a lower frequency and a lower pitch. Again, the ambulance itself, if it's stationary, would be making the same sound. So how does this relate to light? So if a light source is approaching you, we're going to expect the waves to be a higher frequency, a shorter wavelength, and a higher, basically a pitch in a sense, but higher frequency is what we're going to be looking for. And in terms of visible light, that means it's going to be shifted towards the shorter wavelengths, which are the blue wavelengths. So if I have a light object coming towards me, that light is going to appear bluer than it normally would. Whereas if the light source is going away from me, the light from this object is going to appear to be shifted towards the red side of the visible spectrum. So when astronomers look out at the sky and they look at objects, are the objects stationary? Are they coming towards us? Are they going away from us? What did they find? And as scientists looked at galaxies beyond our Milky Way galaxy, not just the stars in our galaxy, the galaxies beyond our galaxy, they found that wavelengths of these galaxies, of distant galaxies, were redshifted from where they were supposed to be. Now, how do we know that light is redshifted? Well, remember when we said that different elements have different chemical signatures? So if I were to look at a different galaxy, I would notice that that light is going to be offset here. So you can see here that this color band right here has shifted to the red side here. All of these are shifted this way. This happens to be from a galaxy that is 1 billion light years away. But it is redshifted, which means that the distance between our galaxy and this galaxy has to be increasing. This object has to be moving away from us, or we're moving away from them. It's 6 of one, half dozen of the other. It doesn't matter. We're moving apart from each other because I can tell that these wavelengths have been shifted. And what they found is that not only was that galaxy redshifted, almost every distant galaxy was redshifted. And what's crazier yet is the farther away the galaxy was, the greater the redshift was. So as I look at galaxies of increasing distance, you can see that this redshift keeps increasing over time. Okay, in fact, this redshift increased so much it went off the visible spectrum. And so this is the most distant galaxy. This is the closest galaxy to us. Okay, and so all these objects in space are moving away from each other. So what can we conclude from this? Okay, because of these redshifts, we can figure out that all galaxies are moving not only away from the Milky Way, but from each other. Well, how do we know this? How do we know that the Milky Way isn't the center of the universe and that everything's just moving away from the Milky Way and that everything kind of started here and everything's moving away? Well, imagine if I drew some dots on a balloon. Not one of these dots would we consider to be the center. It's not necessarily that one, it's not necessarily that one, not necessarily that one. None of these is the center. I blow up this balloon, the distance between each of these dots increases in size. Okay? So that means, in this scenario, if we compare the universe to a balloon, that all galaxies and clusters of galaxies are moving away from each other. Space is expanding. The universe is getting bigger over time. And what's a little bit scary is that it keeps getting bigger and bigger at a faster and faster and faster rate. So here's some conclusions we can draw from this. The universe is expanding, but if we rewind the tape If this is going forward in time, what happens if we went back in time? Which means that at one point, all matter had to be much, much closer together. And because of these redshifts that were noticed, these were some of the first observations that led to the idea that the universe began with a Big Bang. These are not the only observations. These are not, in fact, even the best ones, but they were the first observations that led people to say, hey, maybe at some point in the past, all matter was compressed into a single point, and that this is the progress of time, and that space keeps getting bigger and bigger and bigger. But at one point, all matter and all energy was compressed in a single point. And that is what the evidence, as crazy as it sounds, is suggesting to us. So the ideas I want you to get from today is that the universe is expanding. This is the evidence that there was a Big Bang. And the reason they know that the universe is expanding is because of the redshift of light from galaxies, which indicate that they are moving away from each other. So what I would ask you to do is make sure you understand these notes, and then there is a video which kind of explains the Big Bang, just to put a little cherry on top of your day. Other than that, I hope you understand this material. If you don't, give me a chat. But then we will see you again on Thursday.